Awesome. Yeah, so let me share my screen. Great. So yeah, I hope everyone can see my screen. So welcome to Multimodal Weekly. This is a webinar series hosted by the team at 12 Labs. For context, we are in Series A startup building multimodal prediction models with understanding. For those of you who are new to the series, we've been meeting on a weekly basis over the past 2 years or so. Here are the topics that we can cover every week. New research in multimodal AI and prediction models, innovative application of multimodal in different verticals, different video and multimodal projects from community members in our Discord, and sometimes internal team members talks on how to use our platform and API. And for example, these are some of the content in the session in the past month or so. You can see there are talks from researchers diving into benchmarking video standing, streaming video online to video captioning and modality competition. There are also talks from some of our partners like AWS, Vespa, explaining how to work in conjunction with 12 Labs. So yeah, for today's session, I'm very excited to have two speakers. Actually, Evangelos is going to go first. He also go by Vangelis. He is currently a postdoc researcher at CTU in Prague, and he will present a novel approach for captioning and object routing in video, where the objects in the caption are routed in the video via temporally dense spotting process. And then Cristobal, who's currently not on the call, but should be joining in like 15-20 minutes. He's currently a PhD student at Stanford's Vision and Learning Lab. He will present his work on streaming detection of query event start. So the idea is to identify the beginning conflict events as it's described by a natural language query inside a video with high accuracy and low latency. So you can see the topic of both of this work, right, are very relevant to video understanding, which is kind of our focus here at 12 Labs. So very excited to hear the process and the mechanism and the scientific experiment that Cristobal and Evangelos has worked on for the papers. Feel free to send your question on the Zoom chat for any of you who attend live, and then we'll have a short Q&A session after the speaker finish. So with that, I will stop sharing my screen, and Evangelos, feel free to go ahead and start sharing the screen.
So can you see my screen?
We're actually seeing the presenter note.
Oh, okay. Give me 1 second.
No worries. Yeah, I can see it now.
Okay. You can see it, right?
Yes, we can see it.
Great. Okay, let's start. Thanks a lot, James, for the introduction. Today I will present our work on large-scale pre-training for grounded video caption generation, which is a work in collaboration with work done by myself, Cordelia Smith, and Joseph Sivic. So first, let's define the grounded video caption generation task. It is actually having a video as input. It consists of 3 different subtasks. The first subtask is video captioning, where given the video, a caption is generated. Like this example here, a man is adding ingredients from a bowl and cup into a jar to mix them. In the second subtask, the noun phrases are identified from the caption, where in this case, we have 4 different noun phrases: the man, the bowl, the cup, and the jar. And in the third stage, the model should ground the noun phrases corresponding to objects to individual frames in the video. Now, let's first discuss a bit of the related works in video grounding. And I will talk about datasets in this problem and also like related methods. In terms of datasets, two prominent datasets in this area is VidSTG and HCSTVG, where both contain dense annotations in that there are annotations for each frame in the video, but it's annotations for a single object per caption. For example, you have the sentence on the top, which is from VidSTG, a little boy with a Christmas hat is catching a yellow toy, and the bounding boxes correspond only to the boy, while in the bottom, which is from the HCSTVG dataset, although we have a sentence with multiple nouns, there are annotations only for the first noun, which is the woman. There is also the ActivityNet-Entities dataset, and this is the different dataset and more close to our work. It has annotations for multiple objects per caption, similar to our work, but it has sparse annotations, which means that each object is annotated for a single frame. And as you can see, the man is annotated in one frame, the room is annotated in another frame, while the bike is annotated for another frame. But there are not annotations across multiple frames for each object. And in terms of related methods, there are like a lot of work. There are works suggesting new architectures for video grounding. There are works adapting image grounding architectures to the video domain. There are works doing contrastive learning by training in an unsupervised way on a large number of videos from YouTube. And all those approaches, they have some limitations. First of all, they cannot generate text because the text is given as input to the model, and they predict bounding boxes only for a single object per video. They cannot predict bounding boxes for multiple objects. There is also this work, which is called grounded video description, which performs both captioning and grounding, similar to our work, but the captioning and the grounding is performed in two independent steps rather than simultaneously, and the objects are grounded sparsely, so there are predictions for objects only for very few frames in the video. While we want to do captioning and grounding simultaneously, and we also want to ground objects densely. Now, our contributions in this work is that we propose a large-scale automatic annotation method for getting captions and grounded noun phrases in the video from the caption. We apply this automatic annotation method on the how to 100 million dataset, and we get a large-scale automatic annotated pre-training dataset, which we call how to ground 1 million. We propose a new grounded video caption generation model, which we call GROW. And we also propose a small scale but highly accurate manually annotated dataset, which we call iGround. And this dataset is very good for fine tuning and evaluation. Using those datasets for pre-training and fine tuning, our proposed GROW model, we get state-of-the-art results on 3 different datasets. On the proposed iGround dataset, but also on the VidSTG and HCSTVG datasets, which are for spatiotemporal sentence grounding. And finally, we offer extensive ablations for the importance of the scale of the pre-training dataset, but also of other important components of our model. Now let's start with the automatic annotation method. It consists of 3 different stages, and just to remind you, the goal is given a video to get automatically annotations for captions and to ground the sentences in the caption, to get also bounding boxes for the noun phrases in the caption. So in the first stage, we perform frame-wise grounded caption generation. So we start to... Sorry? Okay. Yeah, so we start, you can still see my screen, right?
No, I think it's disconnected. Can you share your screen again?
It was disconnected for a bit, but I think now is... Can you see it now?
Yeah, now we can back. Go ahead.
Okay, sorry. Sorry for that. So yeah, in the first stage, we perform frame-wise grounded caption generation, where we run an image level grounded caption model to get noun phrases, bounding boxes, and caption descriptions for each frame in the video independently. But as you can see, you know, these are disjoint, so we have different descriptions for each of the objects, but we want to, and different captions. We want to get a single caption for the whole video, and we want to get a single noun phrase consistently throughout the video for each object. So we propose 2 extra stages to address these issues. In the second stage, we use an LLM and we aggregate frame level captions into video level captions. And we do that by extracting the subject, verb, and objects from the caption. From the caption of each frame, we give this as input to the LLM. And as we can see, the LLM gives us output. In this example, a woman is drinking a beverage from a glass, which will be the video level caption. Finally, in the last stage, we use this output caption, and we again use an LLM, and we ask the LLM to classify all the noun phrases from the first stage. So this would be, you know, the woman, the green beverage, or the woman and the glass of green liquid in different frames. And we ask each of those noun phrases to be classified using the LLM to either the woman or the beverage. And the LLM, as you can see correctly, classifies them. And the result is having a video level caption and also a consistent bounding boxes and noun phrases throughout the whole video. And yeah, we can apply this method, as we can see later, to generate a large-scale pre-training dataset. So we apply this method to the how-to videos from how to 100 million dataset, which is a dataset of 100 million video clips from YouTube. We randomly sample 1 million video clips from this dataset, and we use the start and end timestamps from a different work, which is called how to caption, because it provides more accurate start and end times of events. We downsample the videos to 5 frames 5 frames per second so that we can run our method more efficiently. And a bit about the statistics of the dataset, it consists of video clips of 8 seconds long with a spatial resolution of 455 by 256. And finally, the proposed how to ground 1 million pre-training dataset contains 1 million videos, 1 million captions with 3 million noun phrases, and the captions contain 18K unique terms and 142K unique noun phrases. Finally, the dataset contains 43 million annotated frames with 80 million bounding boxes. And here in this table, there is also a comparison with other datasets where the datasets that we discussed before, VidSTG and HCSTVG, they have annotations for multiple frames. but they don't have multiple object grounding. They ground a single object. While the ActivityNet-Entities that we've seen before contains annotation for multiple objects per caption, but not across multiple frames for a single frame per object. But our dataset, our proposed how to ground 1 million dataset, and the manually annotated iGround dataset, they contain both annotations for both multiple frames and multiple objects per video. And the automatically annotated how to ground 1 million dataset has the largest number of videos across all the different datasets, and also the larger number of instances, so the larger number of annotated bounding boxes. Now let's quickly discuss the model that we propose, the Grove model. So it consists of two different encoders, one for captioning and one for grounding. The encoder for captioning has a smaller spatial resolution so that it fits within the LLM's context length, while the grounding video encoder has a larger spatial resolution to get the fine-grained spatial details of where objects exist. We freeze the backbones from both the global video encoder and the grounding video encoder. But importantly, we add spatiotemporal adapters to model the video and extend the architecture to the video domain. There is an LLM, which is connected to the global video encoder, which predicts caption for the video. So given this video, the LLM predicts, in this example, the caption, a person is washing a dog. And it also predicts the locations of the noun phrases in the video, in the caption. In this case is the person and the dog. So given the noun phrases that are predicted by the LLM, we use the hidden states corresponding to the noun phrases. And these are color-coded here with green and red. And this go as input to the bounding box decoder. So the bounding box decoder takes as input spatio-temporal features from the grounding video encoder, and also queries about each object and performs cross-attention to get representations for each object, for each potential object in the video. And then we have two prediction heads, a bounding box prediction head, and very importantly, a novel temporal objectness head, where the temporal objectness head predicts the presence of an object in a specific frame, because in this data set, there is the problem where objects appear and disappear. And while other models cannot predict when objects disappear and then reappear in the frame, our model can predict this using the temporal objectness head, which, as I will show later, improves the results and the precision of the model a lot. We finally also propose the iGround datasets, which, as I said before, is manually annotated. You can see some video examples here where I've put two videos next to each other. It consists of 3,500 examples, and we split them in train, val, and test, where the training set contains 2,000 examples, the validation set 500, and the test set 1,000. We have temporally dense annotations and also multiple objects per frame, and this dataset is suitable for fine-tuning and evaluation. The metrics that we use for evaluation is Meteor and Cider for the captioning quality, AP average precision at 50% for the grounding quality, and also a modification of recall, which is again for grounding. And I say a modification because it consists not only the overlap between bounding box predictions and ground truth predictions, but also the similarity between the predicted noun phrases and the ground truth noun phrases. And I will talk also a little bit about the statistics of the other two datasets that we use for evaluation. The VidSTG dataset is the dataset for spatiotemporal sentence grounding, as I mentioned before. Consists of 10K videos with 79 type of objects, and it has 5K videos for training, 600 for validation, and 700 for testing. And the metrics in this dataset, we use the proposed SIOU metric, which is defined as the IOU across frames between the predicted and the ground truth bounding boxes for the target event. And the ActivityNet-Entities dataset is a dataset for grounded video description, where there are 15K videos and 52K sentences with 158K noun boxes in total. The metric used here is the F1 score, which, as you know, is a combination of precision and recall. The way that it is defined is they have different versions of F1. They have F1 null, which is where a region prediction is considered correct if the noun phrase is correctly predicted but also correctly localized. The F1 log, which considers only localization accuracy. And in those metrics, the accuracies are averaged across noun categories. And then they also have F1 null per sentence and F1 log per sentence, where accuracies are averaged across sentences rather than noun categories. And now, here are our results. We essentially get state-of-the-art results across all three datasets. One important observation. So, yeah. Here in each dataset, as we can see, we have the pre-training performance, and the pre-training and fine-tuning performance. So in the proposed iGround dataset, we have the performance of pre-training, the performance of fine-tuning, the performance of pre-training and fine-tuning. While in the others, we have fine-tuning and then pre-training and fine-tuning. One important observation is that performing pre-training and fine-tuning is better than fine-tuning only. And this is consistent across all datasets, which shows the importance of using our large-scale pre-training for pre-training the growth dataset, and just using manually labeled data for fine-tuning is not sufficient. And also, I would like to discuss the scaling behavior of our model. What we did here is that we increased the size of pre-training data starting from 1,000 examples to 1 million, going up to 1 million examples. And we do this both for the fine-tuned model, which has been pre-trained on our pre-training dataset, but also on the pre-trained only dataset. And we can see that in both cases, the performance increases with the increase in the pre-training dataset size. And this behavior is consistent during both pre-training as well as when we fine-tune after pre-training, which shows that having more pre-training data is beneficial even if you have fine-tuning data. And in the future, we will consider going to even larger scale data. And the temporal objectness, we check the importance of the temporal objectness, which is for predicting objects that temporarily leave the frame and possibly reappear. We increase the threshold of the temporal objectness, so to have more accurate predictions. And by increasing this threshold, the average precision improves with only a minor drop in recall. So, and the result of this is that we are able to better model objects that temporarily leave the frame with only a small sacrifice in recall, but getting significant gains in precision. Here are some qualitative results from extracted frames overlaid with bounding boxes along with the captions generated by the model. And some interesting cases that I would like to discuss is, for example, in this example, where the generated caption is a person's hand is making a drawing on a whiteboard, we can see that the temporal objectness works well because the hand of the man appears only in the second and third frame, and it is correctly predicted only in those two frames, while there is no prediction for the person's hand in the other frames. And this is thanks to the temporal objectness head, which can predict the presence of objects. And there are other cases like this, for example, here where the prediction is a person's hand are using a screwdriver to tighten something. Both the person's hand and the screwdriver are predicted only in the first, third, and fourth frames. Other important observations is that our model can ground multiple objects, like in here or here, where it grounds, as we can see, up to 4 objects. And that finally, that the bounding box predictions, as we can see, they are smooth, they are spatio-temporally consistent across frames. And we can have a look at a few video results as well. Yeah, some of them are from the same videos, but there are also other additional videos to see how the model actually performs in a video rather than only in a few selected frames. As I said, you can see here how it predicts, it grounds 4 different objects, and the results remain spatio-temporally consistent throughout the whole video. And similar here. This is actually also another interesting case because there is significant viewpoint change, and this is the case a lot of times in those in our proposed iGround data set. So you can see that the woman appears in very different viewpoints, and despite the change in viewpoint, the model is able to predict the bounding box of the woman and the rest of the objects correctly through the different viewpoints. That was the example that I've also shown before, where the temporal objectness helps to predict when the hand appears. And I think this is the last one. And I would like to thank you a lot for your attention, and I'm happy to take any questions if you have.
Awesome. Yeah. Thanks, Vangelis. I think because we're running a bit out of time, past the hour, let's do question asynchronously via the chat. So attendees, if you have any question about this work, feel free to put on the Zoom chat so that we can do asynchronous Q&A. Yeah. With that, This work for you, Vangelis? That we do Q&A via the chat. Yeah. Let's pass it to Cristobal. Yeah. Go ahead. Feel free to share your screen and go ahead with your presentation.
Can you verify that you can see my screen?
Yes, I can see.
Awesome. Cool. I'll just jump right into it then. Hopefully people don't need a rest after that great presentation from Evangelos. That was a lot of content in a good way. Cool. So anyway, this is my own work, streaming detection of queried events start, somewhat related in that, you know, all these different presentations are connected by the multimodality, I guess, general theme, but a little bit different, I hope, from what most people are working on. And this is because we sort of motivated this work initially by looking at, you know, where we think the field is going, but also consumer market products, right? Just where we think AI will be in a couple of years, and not just where it is nowadays. And there's maybe like an important distinction to be making, I think, when we think about videos and video models and where they're actually deployed. And one of these is that video models used to not be capable enough maybe for some of these more real-time applications, but also the people and the labs and this is industry and individual labs, but you know, like academic labs, but seem to be pushing for more of a offline sort of video analysis kind of pipeline, which is obviously very useful if you're Google and you want to analyze YouTube videos, or you know, if you're a lab and you want to generate a new data set from something or provide some additional insight for a company, blah, 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 blah. But it's very obviously not a kind of model that you could deploy for real-time applications, because from its base, a model that was made for sort of offline analysis, like at the end of the day, sort of you look at the entire day's video kind of analysis, that kind of model does not work well for a like real-time scenario. And so we're looking at, you know, how these Ray-Ban glasses, like they now have a name, Ray-Ban, but when we started this project, they didn't really exist, but how Facebook was pushing for this sort of project area, like demo glasses that I'm showing on screen. And this Dataset Ego4D that was just then like being presented, where people were asked, like annotators were asked to wear head-mounted cameras, mostly GoPros, while they were doing their day-to-day activities. And we identified that maybe these cameras that were head-mounted and egocentric were going to be in some of our products, or just in more sort of embodied applications in the future. And like one of these questions that we started asking ourselves was, well, what if Siri had access to our camera? And I know it's like maybe kind of a more obvious question now when we have ChatGPT with camera-enabled assistance, but we started thinking about like, okay, if our cameras were real time and our assistants had this access to real-time feed, what are the kinds of questions or tasks that we would want our assistants to solve for us? And so there's a certain number, obviously, of like different applications that you would want to maybe solve with these kinds of models. The more obvious ones are like what I was just saying, the AR assistants, but then there's also, you know, any sort of embodied application. Self-driving is one of these, obviously, you know, a model that is driving around by itself, or like has access to a car and is controlling the car so that the car drives around, needs to identify when the light turns green, when someone starts crossing the street, etc. There's all these different events. And much in the same way, robots, because they're also embodied, might need to identify, you know, when it's safe to vacuum a house. For example, it'd be great if Roomba could understand that while I'm watching TV, it's a bad idea to like go and disturb me and just make a bunch of noise. And that seems kind of like a trivial thing to implement, but most of our video models, again, are just emphasizing this like post hoc, like after the whole video has been recorded sort of application. And therefore, you know, even if you have a very capable camera on your Roomba and your Roomba has enough processing power, like you're not going to know that the Roomba shouldn't have been bothering the people that are watching TV until the very next day when you identify that that event. And so not to pretend that we're the first people to look at obviously streaming video models, but with their like most of the models, I don't want to call them antiquated, but they seem to be sort of stuck in this one of multiple labels classification, in the same way that, again, not to call these antiquated, but like image classifiers will classify to one of 1,000 classes, and that's okay, and it's generally very useful, but it's more useful for practitioners and people that are building products out of these things if you can specify the actual events that you want to detect in the case of video, or the objects that you want to classify. And it's particularly useful when looking at video because the action space, the space of all possible events is so large. So it's not just, a dog, a cat, it can be a dog looking at a cat or two dogs chasing each other. So it's just the explosion that occurs when you have multiple nouns and you have verbs that connect them is such that like we couldn't have any fixed number of classes, and therefore we decided that we had to be looking at natural language queries. And in particular, we're going to focus on detecting the start of an event described by language in a video, but you could obviously change that a little bit without changing the architecture too much. So hopefully that's enough motivation. I'll run over like some of our very old work, I call it here, but the first works that we did in this were sort of like 2021, 2022-ish, like Slip had just come out. And we had an architecture that kind of worked, and we could evaluate it on a data set. The way it worked is just sort of recurrent model that kept looking at like different frames of the video, sampled at sometimes at a constant frame rate, and it would try to identify the moment at which an action starts. In this case, an athlete runs fast and long jumps into sand. You want to detect when that event occurs in the stream. And there's multiple different videos, and your model basically looks at the whole stream and can make sometimes multiple predictions. The multiple prediction aspect is necessary because there's sort of an inherent ambiguity. Because you don't have access to the whole video, you don't know if the event that you're looking at is the best fit, and therefore you should allow for multiple predictions. So yeah, we had this model, and it kind of worked, but the problem we had is we didn't have a decent data set to train it on. Why is this? Well, we were sort of looking at Ego4D, so this had like most of the characteristics that we did care about, mainly egocentric camera, and just temporal annotations that we could translate into like detection supervision for training our models. In particular, we had these like visual queries, language queries, and moments queries, and Ego4D NLQ. But the problem there was that none of these annotations were guaranteed to be like the only instance of, for example, the how many cups of sugar did I add? Like there could be several instances in the video where sugar is being added. And because we needed there to only be one, so we could supervise the model to like when analyzing the video in a streaming fashion, say, no, the event hasn't happened until it actually happens. We sort of needed this additional supervision of, whereas every time that any of these queries that are temporally annotated in the video, like we need to know every instance of them occurring, not just a single one. And so one of the things that you could do is you might nowadays think, oh, let's just use an LLM or some captioning model and combine both of these in order to identify if the event has occurred multiple times. So sort of do offline analysis of the video to generate like all these pseudo captions and then clean them up to generate a data set that is online meaning streaming. Hopefully I didn't lose any of you there, but the main issue back then is again, like the same thing that I'm showing here, that the annotations sort of had overlap or were sometimes repeated. But we tried to fix this with GPTJ because that's when we started working on this. And GPTJ, for those who remember, was a 6 billion parameter GPT-2 clone made by Eleuther AI. It was good for the time, but it's obviously, terrible compared to any of our current models. And so we sort of had to put the project on the back burner until finally, with GPT-4, we decided that we could come back to revisit this project. And this is what the data pipeline with GPT-4 looks like, and it's so much more complex, and it works great. And this is how we actually made this project a reality. But essentially, we can take in the captions for the video, which is what's being shown on the left side of the figure. and then any of these events, for example, the annotated ones that I was showing before, the natural language query ones. And through a series of just prompts and filters, you can identify if like what the actual event that the NLQ was referring to, like what it is. So we sort of do something similar to what Evangelos was just saying. We use an LLM to extract like the main event from a query. Then we need to check if this event is grounded in the captions on the left, because we will use the captions in a second to identify if the event has already occurred. Therefore, it has to show up in the captions when it's occurring, when we know it's occurring, but also it has to not show in the captions anywhere else. If it did show up in like a prior moment in the video, then you need to generate the query such that it is specific. So it has to be non-ambiguous, and you can just add additional qualifiers until it's non-ambiguous, right? Like when is the second time that blah happened already makes it non-ambiguous, because the second time is a single instance and not, it can't be confused with the first one. And so we use LLMs to generate this data set. We take ego for D annotations, NLQ, and moment annotations. We pass them through a series of filters, after which each of these is being converted. This is in the paper, so I won't like explain every one of these stages. But by the end of it, we keep like maybe 30% of the annotations that we also transform into a new kind of annotation, which is what's being shown here. So this is sort of the application that we propose our model should be able to do. Again, focusing on camera enabled assistance. And so, for example, next time I go to a supermarket, remind me to sanitize my hands. Maybe someone cares about that. I don't know. So they would ask their assistant to remind them of this. And therefore, the camera-enabled assistant would have to detect when the person's going into the supermarket, when the event entering the supermarket occurs, so they can be remembered at the correct time. There's better examples of this. So like when I exit the supermarket, remind me to return the shopping trolley, remind me to use a certain loyalty card or maybe a discount coupon or something of the sort when I start paying. Like all these are things that are these are queries that are in our data set that like GPT-4 generated from the ego for D queries. And in the middle bottom row, you can see one of these like non-ambiguous queries. So for example, you can see that in the bottom video, there's two instances of the person watching TV, one at minute 12:02, which is the fourth frame, and one at minute 34 and 45, 34 minutes, 45 seconds, right? So if I just generate a query, which is when I start watching television, remind me to blah, then the model could be confused because there's two different instances. We would be like training the model wrong if we told it that it's wrong to predict that the person is watching television at 12:02. Therefore, we make it non-ambiguous by adding the after decorating the house, which is something that occurs at minute 30, and therefore makes the event non-ambiguous and decidedly pointing at the 34 minutes 45 seconds instance of the event occurring. And I think like the main contribution that we want for that paper is to the data set and the task, and just like sort of motivating people to focus on these more user-facing applications. Think about how we could use these things in hospitals, for example, for real-time detection of seizures, how we could use these things for applications like helping visually impaired people remember where they left their keys in real time, or finding a way to exit a new space that they haven't been in before, etc. So lots of different applications. But we had to include some baselines. So these are the baselines. All this to say, like, they can be improved. They're fine. They're decent. I don't know, but like the hope is you guys, the community, whoever will look at this problem, identify that this is, like something that investors would also be interested in throwing money at, and working on it and improving on these baselines. So basically what we do is we take models like an EVIT-based model, for example, Clip, but also some video models. So EgoVLP, for example, is one of those. And what we do is we intersperse between every layer of these like patchified self-attention blocks of the transformers. Between each one of these layers, we add a temporal adapter. So you can think of it as sort of split space-time attention, except we don't have temporal attention. We use a recurrent aggregation layer between as like temporal component of the split space-time. So the space attention is still the same. We use the frozen clip blocks, but then after every block of clip or EagleVLP or whatever it is, you'll add a block of just some RNN architecture. And obviously you don't need to use like a basic element RNN or anything of the sort. So instead of that, we use more advanced things, basically either 1D convolution, which is what ST adapter had previously explored for action classification. You can use quasi-RNNs, which are kind of look like LSTMs, but are more efficient to compute. And there's also like a code implementation that we released along with our code for this in particular. Or you could even use transformer kind of architecture, as long as it's one of these transformer architectures that has a dual formulation as an RNN, which is usually like the case when you linearize attention. So if you've ever seen like linformer or linear transformer or retentive networks, all of those have sort of this dual like RNN formulation because they've linearized the attention layer so that they can work as like streaming models. And so all of these models you can run with constant cost per frame, which is not the case when you have a transformer, and you could run forever. So we actually evaluate these models on videos up to 2 hours long, because again, they're just RNNs, right? You could run them on a 1,000,000 frame long video. There'd be no issue. There's no temporal window context. There's no memory explosion, etc. And we actually show that a bunch of things with the results. One of them is you need this temporal component in order to get better performance on the data set, which is always good to verify. So the more capable adapters are also good at improving the, the better your temporal adapter is, the better your temporal performance is. And finally, what I'm showing here is one of the additional like metrics that we care about, which is latency. This is to say, we don't just care about performance. We also care about like when we expect like future people that are working on this benchmark to also report metrics like their latency in seconds, so that we can again like focus on using these models for embedded devices and real-time applications and that kind of thing. Yep. So with that, if you guys have any questions, otherwise I'll try to join the Discord. I've had trouble with it, but I can answer the questions in the Discord as well. Thank you.
Okay. Yeah, it's Cristobal. And I actually agree with most of the stuff that you mentioned about the inadequacy of the previous approach and the like commercial use, right? And detection. The internet philosophy also got a lot of commercial requests from users, customers on if you guys do like real-time understanding and then streaming, all those things, right? Especially on use cases around like security, like streaming platform, this kind of thing. So obviously academic work like this that like enable like streaming processing, streaming coder would be super valuable.
I mean, I sort of saw when I was presenting this work, you like reviewers reading the work were maybe less impressed than the people in the actual conferences that hear about the work, and they're like, oh, I can use this for earthquake detection or seizure detection, or like just any of multiple things. And yeah, we hope the community can do a lot more with what we give them.
Okay. Yeah, so participants, we have a question for both listeners. It's about the job. And I know some of this work was pretty old work that you guys working on the past 2 months, like several months ago, right? Are there any like new research work that you guys are currently working on, or like each submission for this year conferences, anything as a follow-up to either the product video caption generation or the streaming event detection? That's really exciting for people to take a look. Yeah, either of you go ahead. You go ahead.
I guess I can speak to two different projects here. For streaming in particular, we're looking at adapting more capable VLMs and making those like streaming capable. The issue there is obviously transformers are not very forgiving in the like let's say like the latency aspect or the context length aspects. And then in submission, hopefully doing well. So let's see. We have to hear back from ICML. There's this interesting project that I led on sort of like estimating complexity of natural language queries about videos. And so it also has the multimodal aspect of, you know, questions and language videos and but we're sort of focusing on trying to like quantify what actually is hard for video models nowadays, understanding that things that are hard for VLMs today aren't necessarily the same things that were hard for our convolution-based models, you know, a couple years ago, or even like masked out encoders based architectures might have different failure modes as, you know, something like Gemini that looks at 1 frame per second. And so automating the discovery of these failure modes is maybe a good way to like explain that. Also, James, it might just be me, but I hear like there's some significant dropout on our at least like on the pipeline that, you know, like you and I are communicating on. I don't know if I've
Yeah, me too.
Yeah, so like if I say something that sounds weird or dumb.
No. Yeah, I can hear you both pretty well.
Okay.
So there's one question
And
from Swat. Oh no, go ahead. Vangelis, do you wanna?
okay, yeah, I can also quickly mention a project that is a follow-up to this work. So, I mean, the university in Prague CTU that I'm working, the team is essentially mostly working on robotic applications, and there are some people in the team working particularly in robotic manipulation, and probably you have heard of VLAs, which stands for Vision Language Action Models, where essentially people use vision and language models to control actions of the robot by giving us input natural language queries. So, for example, a query could be, you know, pick up the glass, or, you know, fill the glass with water, or things, or do the laundry, or fold the clothes, and things like that. We want in the next work to see how we can use the growth model, for example, that I presented today for robotic manipulation, maybe adapting the model itself to robotic manipulation, but also using the model to get some sort of pseudo annotations, because the locations of objects and being able to ground objects with natural language and bounding boxes in the video is very important to VLAs and robotic manipulation. So we want to get some pseudo annotations using this model and train VLAs in a large scale to learn from human videos performing the actions, because the data sets that contains robots performing the actions are kind of constrained, and they're a bit small, and they're also quite tedious to obtain.
Yeah, that makes sense. Yeah, vision language action is pretty exciting, especially on all the work on robotics stuff. I don't know, like foundation models for robotics, right? I think it's pretty interesting domain that a lot of different university labs are investing in that part of. Maybe we can conclude our webinar. If Cristobal can answer the two questions on the chat from Swati. How well do adaptation cross domain temporal granularity?
Should I answer here? I was writing in the chat, but I can just say it.
Oh yeah, you can say it.
Yeah, so actually figure 4 shows the distribution of event durations in our data set. We don't filter by event duration because we want, the same way that I imagine like Swati is asking. We want to be able to detect any range of event durations. So we have events that go from like 1 second to maybe a couple of minutes long. I think the maximum is like almost 5 or 6 minutes long, the event duration. So yeah, especially because we're focusing on the start of the event, which is always going to be a single point in time. We don't impose any limit on the maximum duration of the event that we're detecting. The start is still just going to be a single frame. And the model latency is still going to be the number of frames after the start frame at which you predict. That being said, I don't think that we looked at the like the model's errors with respect to like if your x-axis were event duration, we could have done a better job there at looking at how well the model does at predicting like these different event durations. So that's not something that we report in the data set, but maybe it's something that like I can look into if you care enough to like email me about it. And then question number 2 is how do adapter-based temporal reasoning, I guess these adapters improve safety critical scenarios like anomaly detection CCTV? And so I guess it's improved versus a baseline. So what is our baseline? If our baseline is an image-based model, image-based models are pretty noisy in their predictions. So if you're just looking at how high does clip score this query versus this frame in your CCTV, and like maybe the query is person robbing, let's say, because you want to detect that. So if you're just looking at the raw clip scores and you try to threshold that in order to obtain a prediction, those are going to be so noisy that you probably won't be able to build an actual detector on top of it. So one of the main jobs that an adapter or any temporal layer that you're adding to the model has is to just smooth out the like the predictions from the model. This is especially important when you have egocentric video because camera wearer's head moves around a lot. So even if a particular frame might seem like it doesn't contain any information, if you have a sort of like, if you're carrying along temporal information from the previous frames, you can use that to, again, like smooth out your prediction. The screen looks blurry, but if we were just, like walking around and turning our head, we're probably still in the same place. We're probably still going into the supermarket or whatever. So these temporal adapters are not just important for like keeping a history of what's occurred in the event, in the video, which is something that they do, but it's also very important for just the robustness of the signal and having a more stable prediction come out of the model.
Awesome. I think this is very informative and detailed answer. Security, video security, slash surveillance is like a very common use cases that we see every time. And I think, yeah, ability to temporal reasoning is pretty important.
You know what Gemini's solution is to CCTV type video? So they increase. So Gemini has a 2 billion token context length, which means that Gemini can analyze up to, wait for it, 2 hours of CCTV video. It's ridiculous, 2 billion tokens is, I mean, it's an amazing model, much better than anything I've ever built. So like, don't anyone know what you get mad at this, but it's obviously not well suited for CCTV or streaming applications if you can only look at 2 hours of video, and to do that you need Google level resources to fit 2 billion tokens in your context length.
Yeah.
Is it 2 billion or 2 million? I don't know, one of those. But yeah, so like there's just an obvious space there for models that don't scale quadratically or linear light transformers do, and just improve it by
Right.
adding some state space model layer or linearized attention or RNN or convolution or anything that is slightly more efficient. Or more than slightly.
So state space model like Mamba and what's the other one come together?
I mean, so you usually have like S3, S4, like that's a classic state space model. Mamba's not quite actually a state space model, in that there is like a temporal dependency which they work around. like in the end, it's no less efficient for including it, and it improves performance. But yeah, so something like Mamba can be written as an RNN update, like a recurrent update, and therefore you could just use that as an adapter between like purely spatial attention blocks in order to just adapt those frame models into a video model that can do some temporal aggregation along the temporal axis, right?
Yeah, so we're excited to see how state space model will be adopted in industry. I think a lot of the invention there still happening happening now. A lot of commercial development of the inside transformer yet. I think probably because infrastructure to run, any like model inside transformer is not there yet. I assume so. If we figure out like the CC game and come up with the right engineering practices to train adapters based on specific model, that we very exciting. We sure where we get much better. Maintain the performance one, so like in the game, especially for the expensive application like streaming detection security.
I mean, even if you have a slight decrease in performance, it's maybe still worth it if you can run these models, when the alternative is not being able to run them at all, or needing to stream your video to a whatever, a massive data center on the other side of the world where they have hundreds of TPUs waiting for that one particular video to fit that super long context length. Then like there's a simpler alternative, which is you run a more efficient model that you don't need an entire data center for, which is generally going to be the right answer, I think, for just any embodied application where you also care about latency, right? Because like there's also a connection latency.
Right.
I wonder how our works can be combined, Evangelos. Like there's obviously, especially in robotics and embodied applications, there's like an important need for grounding and event detection that is grounded on like the actual objects.
I think, also another future direction in our case is to also do temporal grounding, because currently the model does, as you've seen, only spatial grounding given the start and end times. I think one like obvious way of combining the two is performing the spatio-temporal grounding, because correct me if I'm wrong, but I can see your work as a specific case of temporal grounding, right? Because given a sentence, you essentially predict like a time in the video. And yeah, this is a specific form of temporal grounding. And I say specific because your queries have a specific format. You ask a question about a specific moment in the video. But yeah, in the more general sense is temporal grounding. And I guess one obvious way to combine it is either in my case that my model would be able to perform spatiotemporal grounding and also generating the caption for the video, while in your case, it would be very interesting if apart from detecting the time in the video, maybe in some cases you also detect the object. Possibly there are different object instances and you want the model to show you the one. Let's say that there are 3 different knives, I don't know, and you were cooking using one particular knife and you want to ask a question when, I don't know, when did I use the knife last time and which knife it was, because I forgot, something like that.
Yeah, it'd be cool. I see this being a model that we add to our future home assistant robots or something of the sort.
Also, yeah. I know we're running about 10 minutes out of time, but thanks again, both speakers, for spending time preparing materials, giving the talk today, and how the content very valuable. The recording of this session should be available on YouTube probably within the next 3 to 4 days. So be sure to share it for you on when it's up, so you can promote it to different channels. And yeah, thanks to attendees for those who joined today and for those who watch it later on. As again, we run this virtual webinar series on a weekly basis. So we're excited about, multimodal lead understanding, application, and research. If you do sign up, register interest for future session. With that, I will, thanks everyone, and hope you enjoy the rest of your weekend. Cheers.
Thank you. Bye.